Okay, so what I'm going to tell you, it's actually the matter of 2 lectures and the results of actually more than 4 papers during more than 4 years. And first of all, I would like to mention my collaborator. This is Boris Altschuler, Lev Yofe, the principal collaborator, Emilio Cuevas of Murcia in Spain, and also important Ivan Haimovich from Max Planck Institute in Dresden, Max Planck Institute for Complex System, and a couple of younger people, Andrea De Luca, who is currently in Oxford, and also our Iranian collaborator from Isfahan. He's an associate to ICTP. And you see, this is a logo, and this is the place. So the question is, old and new simultaneously. This is the question of Anderson localization, and of course, any question of Anderson localization starts with celebrated Anderson Hamiltonian. It is if you consider non-interacting system, and it is the main actually subject of my talk, but in connection with interacting system. So I'm going to use non-interacting system as a playground to figure out what happens in the interacting case. And this is celebrated, as I said, Anderson Hamiltonian, which contains of hopping term over the network of connected sites, and in each site you have an energy that corresponds to this site, and this energy is random. And there could be different distributions of this energy. Important is that they are uncorrelated at different sites and identically distributed, so that the system is statistically homogeneous. And of course, for analytical calculations, people almost always use Gaussian distribution. For numerical calculation, it's more convenient to have so-called box probability distribution. But in any case, there is one number that characterizes the disorder, and this is the range within which your on-site energy may fluctuate. So this number will be denoted as W. So basically, there are 2 parameters here. There is one parameter is a hopping integral, which is supposed to be, in what I will be talking about, it's supposed to be non-random, at least in this lecture today, in some given number, and this on-site energy is random, and so the entire system is random, and the question is, what happens if this manifold is not just one-dimensional, two-dimensional, three-dimensional lattice, but more complicated one, and we will see that in order for this one particle problem to be somehow related with many body problem, you should really have, you should really study localization not on the lattices, but on the graphs. And we will be seeing, we will see it later on. So for those who never had anything to do with Anderson localization, I start from the notion of resonances. So suppose you study the problem for undergraduate quantum mechanics, which is a two-well potential, and the Hamiltonian, which is described by 2x2 matrix, and this matrix is characterized by 2 on-site energies. This is exactly the on-site energy, which we will be considering later on more complicated networks. So there are on-site energies, and there is a tunneling integral here, or hopping integral. And what we know the following, that there are two regimes. The first regime is the regime out of resonance, where the difference between these two energies is much greater than the of diagonal elements. And then the wave function is such that in one the probability sits in one well, and in the other well it is small. And then there is another limit which we call a resonance limit, where these two energies are close to each other, so they are in a resonance, and the condition is that the difference is much smaller than the tunneling integral. And in this case, you have two closed states, slightly splitted. One is symmetric combination of the wave function in both wells, and the other is anti-symmetric combination, and the wave function is sitting, the probability, the square of the wave function is sitting in both wells simultaneously, and this is what is called resonance or hybridization. And then if you consider, let's say, lattice or any other network, then if disorder is weak, okay, I will start with strong disorder. If disorder is strong, then actually these energies, on-site energies, like here, they are fluctuating in much wider interval than this hopping integral, and therefore the resonance condition is a rare event where occasionally two energies are much closer than the allowed range of fluctuations. And in this case, since it is a rare condition, there are not so many resonances, and they are separated by many off-resonance sites, and this is what actually is Anderson insulator or localized state. And if you look at the psi squared of the wave function, then it is confined in some finite region. It has a high peak in this region, but beyond it, it's exponentially small. This is the normal localization. If disorder gets smaller, or so if this guy gets more narrow, or this guy gets bigger, then what happens is that the resonance conditions are easier and easier to fulfill, and you have many resonances, and in the limit you have all sites in resonance to each other, and then we have a delocalized extended state, and the wave function psi squared in the limit where disorder is very weak, it occupies all the available volume, and the only structure that we can see here is de Broglie oscillations, because we usually consider the wave function at high energy, so it has many nodes, but otherwise it's more or less homogeneous spread of wave function over the space, and this is what we call ergodic delocalization. And so until actually very recently, the question in localization theory was about the transition, if it exists, between this situation and that situation, but principally there were only two situations to consider. So if you go to let's say three-dimensional systems without interaction, then the picture is like this. You have at very weak disorder, you have this ergodic extended state. Then at very strong disorder, you have localized state with small localization radius. And in between, if you have systems of dimensionality greater than 2, the lattice, then there is a so-called Anderson transition. So it is quantum phase transition, if you wish. It has many properties of the second order phase transition. And right at this transition point where the disorder is equal to the critical one, the wave function has some special properties because in this case, as in all phase transitions, the correlation radius diverges, and the wave function is characterized by a certain power law dependencies. I will tell in more detail what does it mean. But just on the level of simple look at these wave functions, you see what actually happens is that there are regions of high amplitude, so which are so to say mountain region, and there are valleys. And if you ask what is the weight of such regions where you have high amplitude, it actually spreads from one bank of the system to the other bank, and so the wave function is extended. Again, I will give more exact definition of what does it mean. But on the other hand, there are plenty of the space where... Sorry? This one? This one? No, what is supposed to be is the following, that the system as a Hamiltonian, it does not have any integral of motion but the energy. So this is the simplest possible case. So it is not like, it doesn't have, if you look at the Hamiltonian, there is no any conserved quantities. Yeah, but if you look at deeper, then as it was realized quite recently, and actually some integrals, emerging integrals of motion, which are happening in the localized phase. But this is not a conservation law of the Hamiltonian. So it is something that emerges where the system is in the localized region. So I could tell in more detail about this, but that would be that would lead us far away from the scope of. Okay, this is the situation, the standard situation. So as I said, there is ergodic case, there is localized case, and there is some case which is extended. But since there are plenty of valleys where the wave function is very small, it is not ergodic. The wave function does not occupy all the space which is given to it. What is the main subject of my lecture is the situation, or at least a search of such situation, where such wave functions with such statistics that normally happens only in one point of disorder. The question is, may it happen in a region? So how many phases do we have? Do we have 2 phases or do we have 3 phases? So in connection, on the lattices, the common wisdom says that if it is a lattice of 1 dimension or quasi 1 dimension, or 2 dimensions, then all the states are principally localized in an infinite system. If we have system with dimensionality greater than 2, then there could be 3 different situations, but never a region of parameters in which such special critical wave function lives. Why do we think and where can we expect such situation to happen? So, you know, if it never happens, then I would not be speaking about that. So it means that it happens. And it is important because if there is a region like this, then first of all, there is the second transition. And secondly, this type of wave functions, it actually is different from this one and different from that one and shares the properties of the both. And in particular, since it is non-ergodic, if we find such a situation in many body systems, that would mean that ergodicity hypothesis of what is called eigenfunction thermalization or equal distribution of energy over degrees of freedom, that all will be invalid, and essentially the main basis of the conventional thermodynamics should be revisited. And revisited not only in the localized phase, but in a wider region than that. So that's why it is important. And now let us try to guess where such situation really may happen. And for that, as I said from the very beginning, Anderson localization is a competition between two things, between Hoping integrals, between possibility to spread and disorder which prevents resonance conditions. Now, if you have short-range hopping, let's say nearest neighbors hopping, then if I wish to know what is the transmission probability between two remote sites, then it is essentially, if disorder is big and tunneling is not so big, then this is a matter of high order of perturbation theory, and therefore we have an effective transmission amplitude which is exponentially small, and if we compute now transmission probability, which is the square of that, it will be, of course, also exponentially small. And then the matter is the following, that in order to pass from one point to a remote point, it's a small probability. But nevertheless, it may be compensated by a large number of such remote points. And the matter is, what is the relationship between the number of sites at a distance between r and r+1 and this rare small probability to be transferred between the two sites. So let's consider usual d-dimensional lattice, and what we have in this case, we have that this is essentially the volume, the surface volume, and it goes as a power law, and then we introduce the total number of sites, so the total, the total number of such sites, the size of the system, and obviously this total number is the radius of the system to the power of dimensionality. And then if I want to ask how many sites are in the resonance, so what I have to do, I have to multiply small probability by the corresponding volume, then integrate up to the radius, and then see what happens. And so if I have one function which is a power law and the other which is exponential, then actually two things may happen. So if the sample size is in such a region where the exponent is not yet effective, So we have just increase, a power law increase. Then after this integration, what I obtain the radius to the power of dimensionality, the total volume, and this means that the number of sites in the resonance will be of the order of total number of sites. And this is, as I said, this is the situation like this. I explain you, wait a little bit. I will come to that. What is the nature of, you're asking about the nature of this transition. I tell you because this is, maybe I'm too slow, but I have to accelerate. Okay, so you are too fast, and I'm too slow. Anyway, so what I'm saying is the following, that when this guy is power law and this guy is exponential, then essentially two things may happen. Either the number of sites in the resonance is proportional to the total number of sites, or if the sample size is too large, then the integral will converge, and this number will not depend on the size of the system, and that is the localization. This is situation with localization. So actually we have two possibilities. Either we have ergodic extended state, or we have localized state. And this is where essentially this power law cannot compete other than at small system size with this exponent. But then, as I said, we are interested in the situation where such phase, intermediate phase, may happen. And let's consider the case which actually was the first considered by Anderson to prove that localization exists. This is the Bethe lattice. And what happens in the Bethe lattice is the following, that this volume is no longer power law, it is also exponential. K is a branching number of the Bethe lattice. So this guy is exponential and this guy is exponential. So two exponents can compete much better with each other. And if we do the same thing, multiply this guy by that guy, and then integrate, so what we will see the following, that the result of integration is either something that does not depend on the system size, and this is again localization, and this happens where this logarithm of the branching number is smaller than this lambda. But for me, more interesting case is when logarithm of k is greater than lambda. And when it is greater, then you have an exponent, you integrate it up to the growing exponent, you integrate it up to the system size, and you have this result. And now what I want to do, I want to express everything not in terms of the radius, but in terms of the total number of sites in the system. And then I express the radius in terms of n, plug into here, and what I have the number of resonant sites is proportional to some power of the total number of the sites. And this power is smaller than 1 because, as I assumed, that lambda is smaller than logarithm of k. Otherwise, there is localization. So what is happening here is that when two factors are exponential, then this number of sites in resonance with a given one, it may be a power of the total number of sites, but power smaller than 1. A similar situation happens when we have a system with long-range hops. So, for instance, dipole-dipole interaction or similar, where this guy is no longer exponential but a power law with some power. And the system is a lattice, so it is not a Bethe lattice, but normal lattice, d-dimensional lattice. And then we have two guys power law. This one is power law, and this one is power law. And again, they can compete efficiently with each other, and the analog of this expression will be then power law in the system radius, and then I express this radius in terms of the total number, and for the situation where this exponent is smaller than dimensionality of space, I have again the same situation. I have the situation where the number of sites in the resonance is proportional to some number of to some power smaller than 1 of the total number. So there is, of course, some cheating here. The situation is not so simple. Otherwise, it would be already a theorem that if we are on a Bethe lattice or with power law hopping, then there is this non-ergodic extended phase. Cheating is in the following, that I have computed the number of sites in resonance with a given one. So I have chosen one of them and found resonance number of sites in resonance with it. And this was correct. But what I need the total number of sites in the resonance. So I have, in principle, to take all the other sites and find sites which are in resonance with all of them. So I started from this one, I found all these red spots, then I should take any one red spot and find sites in resonance with it. And those sites are the blue sites here. So if it happens that these blue sites do not coincide with already chosen red sites, then I will increase the number of resonance sites. So they will be not what I have calculated, but much more. But if what happens that all the if I try to compute all the sites, find all the sites which are in resonance with this one, I will close the manifold of these red sites, and no new, essentially new sites appear, then my calculations are correct. So this means that what I have calculated is actually the minimum number of sites in the resonance, and it could coincide with the real number of the resonance, or the real number of sites, populated sites in the wave function, or they can be smaller. So basically, the problem is non-trivial. It is non-trivial because it may or may not be the real number of sites involved in wave function may or may not be equal to this minimum number. But what we know for sure, that if we are on the lattice, then this d is equal to 1, and so in d-dimensional lattice, it is no way to find such non-ergodic extended state. So one has to look at these other two possibilities in order to find what we are looking for. And now, if that happens, if what happens is this situation, then all the picture of wave functions looks as follows. So your total space is actually a unification of some fractals with fractal Hausdorff dimension d. I will tell much more precisely what does it mean. But to the first approximation, it is a fractal. which contains n to d smaller than 1 sides. And of course, since altogether there are n sides, there should be n to 1 minus d such fractal supports. And on each fractal support, there are n to d different wave functions as in the metal. So if you take a metal and then by linear combination construct all the possible wave functions, so you will have a band, and this band contains so many wave functions equal to the number of degrees of freedom. And so on each support, there are n to d sides, and by linear combination of them, I can get n to d different wave functions which live on the same support. So they share the same support, but they don't come, the amplitude beyond it is much smaller. And so this picture of stratification of the space, it will be then later on, but this is a very principal effect that we have a number of wave functions living on some fractal support, then a number of, so to say, complementary wave functions living in the other fractal support, and so on and so forth. And now let me give you more precise definition of different phases, since the phase can only be defined if I go to thermodynamic limits, so I have to know what happens in the thermodynamic limit. And so if I have a localized wave function, then it has a finite number of the occupied sides. It does not, of course, finite means that it is zero fraction of all the sides. And this is what happens in the thermodynamic limit in the localized function. If it is extended and ergodic, then there is an infinite number of occupied sides. Moreover, it is a finite fraction. So this means that the number of the occupied sides is proportional to the total number of sides. And this is the definition of the ergodic function. And then there is, if such situation happens, then there is an intermediate phase in which the number of the occupied sides goes to infinity in the thermodynamic limit, but the fraction goes to 0. So this is, it is clear that all the three cases cannot be continuously connected. So they have different limits in the thermodynamic limit, and therefore there are different phases. Now, why this matters? So far, I just was talking about a search for something that we yet do not know why it is useful. And it is useful for the following reason, that if we think of many body localization, then, as was first pointed out by these authors in 1997, and maybe even before, in the theory of complex nuclei, then what actually happens in many body solid state physics is the following. We have a ground state. Then if we excite it, we have one particle excitation. So this is the usual story of describing metals and things like that. But then, if I apply interaction to such a many body wave function with one particle excitation, then interaction leads to creation of electron-hole pairs. So it is actually the one particle, if I cut it in this way, So one particle creates electron-hole pairs, then second application of interaction also creates electron-hole pairs, and what happens is that the structure of the Hilbert space is clearly of the three nature. So each time there is a branching creating two particle hole excitation, and therefore it is believed that a general feature of the Hilbert space in many body system with two-body interaction is the structure of the tree. And therefore, what I am asking for and what I am studying is not simply of academic interest, but it has to do with understanding of what is happening in the many-body situation. And now let us see what actually are the main features of the many-body interaction as compared to usual Anderson localization on lattices, on two-dimensional, three-dimensional, one-dimensional lattices. And the difference are, in fact, three. So first one, as I told right now, that there is a tree-like structure in many-body situation, in many-body Hilbert space. Then, of course, many-body means many bodies, so we have many indistinguishable particles. And so there is Fermi or Bose statistics. This is the second difference between single body and many body. And the third important difference is the following, that if we have, let's say, a spin chain, then usually we have as many random variables as the number of spins. So if we have a chain of some length, then the number of random variables, independent random variables, is L. But the Hilbert space is exponential in L. So this means that the number of random variables is logarithmic in the total number of degrees of freedom. And it is therefore much smaller than the total number of degrees of freedom. But if we look again and come back to the Anderson model, here what we see the following, that we have some manifold of the sides, and each side contains a random variable. So there are n random variables, as many as the total number of degrees of freedom. In many body system, it is not the case. The number of independent random variables is much smaller. This means that effective disorder in many body situation is much stronger correlated, and one has to address this question very seriously if one wants to really do some analytical work. What I will be talking today about is only the first part of these three sort of important features. I would like to know what comes from the fact that the many-body Hilbert space resembles single particle coordinate space, but in case of a tree-like graph. And now, what is the archetypical example of the tree-like graph? It is the Bethe lattice. In this case, it is with branching number 2. But Bethe lattice indeed has tree-like structure, but it has a great pathology when we wanted to use this as a toy model for many-body localization. Namely, the finite fraction of all the sides is on the boundary. And what is the boundary in the many-body Hilbert space? It doesn't have a meaning. So what would be a good model is the one that has a tree structure, but it doesn't have the boundary. It doesn't have the boundary. And such structure is known long ago. In particular, people in spin glass community, they use this structure for ages. And this, roughly speaking, means the following, that you connect all the boundary sites with each other with the same coordination number. And the non-trivial thing is the following, that this process is actually creates not so many defects. So more precisely, take n capital sites, and then make connection of each site, let's say, with 4 others at random. And then ask a question, is there an efficient algorithm to produce such structures? Then how many possibilities we have, and then how many defect structures we produce when doing so. And the non-trivial answer is that actually there is an efficient algorithm that this algorithm produces minimum amount of defects, and such structure indeed is not a rare event, but it is predominantly happens so that if I start this process, it ends up without defects in the coordination number. Yeah, I'm going not only it is not only practical, because this guy is statistically homogeneous. It doesn't have a boundary. So what happens is that if you start from any side, you first see the tree structure for a while, but then it closes on itself. And this closure on itself means that if I take any other side, then I will see statistically the same feature. So it will be also tree-like until some what is known as diameter of the graph, and then it closes. So it is of principal importance that that this is statistical homogeneous manifold, and this is not.
But yes, but I mean, if you consider that infinite system, I mean, there's a infinite Bethe lattice.
Impossible because what I'm going to do, I'm going to study the normalized wave functions. Normalization fails if you go to the infinite system, and this is the reason why mathematicians didn't like such object, because they have been talking about absolutely continuous spectrum, pure point spectrum, and then singular continuous spectrum, but they didn't like to do the procedure that I'm doing, considering finite system and then doing the limit n to infinity. Because if you do it from the very beginning, you have zero amplitude by normalization, and you cannot answer a question, what is the amplitude, because the difference between the valley and the height is proportional to the amplitude. Okay, so now let us work out a language how to characterize such non-ergodic extended state. And since the picture is more clear when there is a two-dimensional case, but in fact all the formulas are valid for any manifold, any graph. So the characterization goes this way. Suppose we have some profile of psi squared in a lattice system. So for each lattice site, we have some psi squared. Now, let's do the following. Let us parameterize this psi squared in the following way. So this box has n sides. The wave function is normalized. This means that in one single side, it cannot be larger than 1. Therefore, and it is positive, of course. Therefore, I can always parameterize it in this way. I take the number of the sites and raise it to some power minus alpha, where alpha is greater than 0. In this way, I can parameterize all possible instances. Now, what I can do, I can take a certain level, which is this n2 minus alpha, and ask a question: what is the map of the region where psi squared is greater than this level? And the answer is that if I deal with this non-ergodic extended wave function, the map is a fractal. So the dark region corresponds to regions where psi squared is greater than this chosen level. And then one can find the number of sites on this map, and since it is fractal, it has certain Hausdorff dimension, which is actually a function of the level. So if I take alpha, which is smaller, this means that the level will be higher. Then just intuitively it is clear that you have sparser fractal than when the level is lower. And this means that the fractal dimension does depend on this alpha. So it is some function of the alpha. And this is one possible way of characterizing this situation. So you choose the level n2 minus alpha and find the fractal dimension of the map where psi squared is greater than this level. There is a different way of characterizing which is equivalent, in fact, and this is the following. You take the psi squared, the amplitude of the wave function in a given site, and then you raise it to some power q, which is just a variable. You raise it to some power, and then sum over all sites. It is clear that the higher this q, and since psi squared is smaller than 1, then the more contrast will be the picture. So it is like raising this level up. So this alpha and q are obviously related, so that okay, so this is clear. The question, the result is that if this is a fractal, everything should be power law, then this guy is inversely proportional to some power of this, some function of q. But then there is normalization. Wave function is normalized. So if I take q equal 1, this is a normalization condition. It should be equal to 1. So this means that this power here, it should be 0 when q is equal to 1, just by normalization. And you can always represent it in this way. And this guy dq is also sort of fractal dimension. And it is not just unique, because in this case it depends on alpha. In this representation it depends on q. And so we have not just one fractal, we have a multitude of fractals. And this is known as multifractality. So the usual situation is that it is not just one fractal, it is some spectrum of Hausdorff dimensions, f of alpha or d of q. Now, it's sort of irresponsible slide, because it is more like question than like an answer. So yesterday we have a talk by Schmull-Fishman, who was talking about mixed state of the dynamical system, and it has, as he explained, some hierarchical structure. And in my case, when I am studying quantum wave function, which is not semi-classical in any sense. Nevertheless, I have also the hierarchy. I have power laws, and therefore I have hierarchy. And the question actually, as long-standing as this picture itself and the problem that Shmuel has discussed yesterday, is whether this is the same phenomenon or I mean, whether this quantum map is just a manifestation of this Poincaré section or they are different phenomena. So this is the question. My personal opinion is that these are very closely related, and simply this is a semi-classical situation and this is not, but this is something which is highly discussable. And now I have few minutes, maybe 4 or 5. I just tell you a little more about characterization. So I told you about characterization in terms of f of alpha. I told you characterization in terms of d of q. And now I tell you that in fact it is if this f of alpha has to do with the distribution function of the logarithm of psi squared. So all what I have been talking about before implies that your the distribution of logarithm of psi squared is possible to represent in such a way that this is exponential, then this n will be logarithm of n here in the exponent, and then some function of the argument divided by logarithm. So it is a very special structure. So you have logarithm in front of f in the exponent, and you have logarithm in the denominator in the argument. And such type of distribution is actually known in as large deviation function. So it was known in spin glass theory, in many other things where strong fluctuation happen. So there are some models in which you can derive such type of the distribution, but in fact it is some class of distributions which generalizes central limit theorem. Because if this function is just quadratic function, so you have central limit theorem. If it is linear function, then you have power law distribution. So in fact, this function essentially interpolates between quadratic distribution, which is central limit theorem, and a linear distribution, which is extremely strong fluctuations like, you know, sand piles, like self-organized systems and things like that. And if you have this type of the distribution, you can connect this f of alpha and this power which stays here, and this is simply a matter of doing the saddle point integration. So the moment is given by such an integral, and since logarithm of n is large, you can do the saddle point integral here, and you find that this tau of q and f of alpha are related by Legendre transformation, and it is simply because in order to find the stationary point, I have to differentiate with respect to alpha and so on. So this is the property of this distribution. So basically, I told you about the language of how to characterize this situation. I told you where to look for it, and next time on Friday, I will tell you about the model in which it is proven that such phase exists. And I tell you about numerics on this random regular graph, which is numerics, which is not a proof, but you will judge yourself how convincing this numerics is. So thank you very much. Uh,